So on the last slide we found the potential by adding up the potential or the voltages from various charges. Suppose we didn't know what the charges were, but we knew what the electric field is. It turns out we can also find the potential by integrating the electric field. Now, thinking just strictly the definition of work, which is again going to be the change in internal energy, that's going to be the integral of the force dotted with dl. And we also know that the force can be written as the charge multiplied by the electric field, again dotted with dl. Now that charge Q naught is actually going to be equal to is just a constant, so we can pull that out of the equation and say that the change in internal energy is going to be Q naught multiplied by the integral of the electric field dotted with dl. And if we divide both sides by Q naught as such, then when Q naught goes away, we know that the potential energy divided by Q naught is also known as the voltage. So this is going to be the change in voltage is simply going to be the integral of the electric field dotted with dl. Now, of course, we're going from one point to another point, so we're going to be integrating from A to B, and this is going to be the voltage from A to B is simply the integral from A to B of the electric field dotted with dl. We can use this by taking a quick look at example 23.6, where we're asked to find the electric field at some point r. Well, we can say, well, I know that the change in potential from A to B, which is going to be equal to the voltage at A minus the voltage at B, is going to be the integral from A to B of the electric field dotted with dl. If I have a point charge, as we have in example 23.6, then dl is simply going to be radially outwards, which is also in the same direction as the electric field. To find out what it is at B, or at A, what I'm going to do is I'm going to take it relative to point B and set point B at infinity. I know that the voltage at infinity is going to be equal to 0. So what I'm left with is the voltage at A minus 0 is going to be equal to, A is actually just going to be some radius away, r, integrate to infinity. The electric field is going to be kq divided by r squared in the r hat direction, dotted with dl or dr, which is going to be also in the r hat direction. They're in the same direction, so really I'm left with the voltage at A is equal to the integral from r to infinity of kq divided by r squared dr. And we know the integral of 1 over r squared is going to be negative 1 over r, so that's going to be equal to kq divided by r. It's going to be negative. We're going to evaluate this at r and infinity. If I evaluate it at infinity, I know that it's going to be equal to 0. So what I'm left with is it's going to be 0 minus negative kq divided by r, and it's simply going to be equal to kq divided by r, which is what I expect it to be. We can, of course, start combining some of this electric potential energy with some of our knowledge from Physics 241, which I'm sure you remember perfectly. Example 23.7 does this, where we have a dust particle that is released from rest at part A, and we're asked to figure out what the velocity is at point B right here. It's sitting between two charges. We know that it has some mass and some positive charge, so it's going to feel a repulsive force away from the positive charge, and it's going to feel a attractive force towards the negative. So, one thing that we can't do, unfortunately, because the force goes like 1 over r squared, the force is going to be constantly changing. So that makes using Newton's laws particularly difficult. However, what we can do is we can use energy conservation and say, well, I know that this potential energy that this object has at A is simply going to be equal to its charge multiplied by the voltage at A. The potential energy here at B is also going to be equal to its charge, Q naught, multiplied by the potential at B. And I know that the energy at A must be equal to the energy at B. Energy is and has always been conserved. So the energy is going to be the sum of the potential energy plus the kinetic energy. Both of these are at A. And then the potential energy at B plus the kinetic energy at B, which is related to the velocity, which is what we're really interested in. It's released from rest, so it has no potential energy. And really we're just left with the charge multiplied by the voltage at A is going to be equal to the charge multiplied by the voltage at B plus 1/2 mass of the particle velocity squared. Make that a lowercase v just to make it a little bit more clear. So really the charge multiplied by the voltage difference, voltage A minus the voltage at B, multiply both sides by 2, divide both sides by mass, and take the square root, and we're left with the velocity of the particle at point B. What we can do to figure out the voltage at A and the voltage at B is simply to do kq divided by the radius of A, add all the voltages up. Same thing for the voltages at B, add them up like I did on one of the previous examples. We have our voltages and we can go ahead and solve for our velocity. So let's take a look at calculating electric potential for some objects that we're already familiar with, following example 23.8. For example, a charged conducting sphere. Now, we know from Gauss's law, we draw a Gaussian surface on the inside, there's going to be no charge enclosed, therefore the electric field must be equal to 0 inside of this sphere. And as we draw our Gaussian surface on the outside of the sphere, we say, okay, we've got all the charge enclosed, electric field is going to die off like 1 over r squared. Essentially, electric field is kq divided by r squared. Now, the voltage, if we look at the voltage for radiuses that are larger than the radius of the sphere, so here we're going to be looking in this regime right here, really the symmetry is the same as a point charge, and so the voltage is going to be dying off like 1 over r, or we could write the voltage outside of the sphere as being kq divided by r. What happens inside of the sphere? That's the question. Well, thinking back to writing the definition as the change in voltage is going to be equal to the integral of the electric field dotted with dl. Inside of the sphere, the electric field is going to be equal to 0, and so the change in voltage is going to be equal to 0. This does not mean that the voltage is equal to 0, it means the change in voltage is equal to 0. So really, the voltage inside of the sphere must be what it was at the very edge of the sphere. So the voltage inside the sphere is simply going to be kq divided by capital R, where capital R is the radius of the sphere. So electric field inside of a conducting sphere is equal to 0. Voltage is not. Voltage is going to be constant inside of such a sphere. Let's take a look at the next example in the book, 23.9. I'm going to do it a little bit differently than what they do. What we're asked to determine is what is the voltage at any given point y. So really we're interested in the voltage at any given point y. If we think about what the change in voltage is, it's going to be the integral of the electric field dotted with dl. So here we're going to be talking from A to B, so we're going to be moving with our dl in that direction right there. That's in the same direction as the electric field. Here we're going to have the electric field going from the positive plate, which is going to be the top plate, down to the negative plate. We know that this is going to be a constant electric field, so really we're left with our change in voltage is simply going to be equal to the electric field multiplied by the integral of dy, or really the electric field multiplied by the distance y. And it's also very common to write the lower voltage to be equal to 0, and so we're left with the voltage with respect to A is simply going to be the electric field multiplied by the distance y away from the bottom plate. So at the bottom plate the voltage would be equal to 0, and at the upper plate the voltage is simply going to be the electric field multiplied by the distance between them. It's also an interesting observation that's going to come into importance later when we talk about capacitors, which is essentially two parallel plates, is you can write the electric field inside of a capacitor to be equal to the voltage difference across them divided by the thickness of the capacitor. So that'll be kind of important in the next couple of chapters here. Another example using some calculus is going to be looking at infinite line charge, following example 23.10. Here we can write the change in voltage as the integral of the electric field dotted with the dl, where in this particular case the electric field is going to be radial. We know that from the last chapter, and our dl is simply going to be in the same direction as the radius, or we can write that also as dr. So the potential difference is going to be equal to the integral of the electric field multiplied, in this case, by dr. Now we know what the potential, or what the electric field is from the last chapter, so we can simply write that here as the linear charge density lambda divided by 2 pi epsilon naught r, and again multiplied by dr. We can pull these constants out, and we're left with the integral of dr divided by r, which is going to be a natural log. So our change in voltage, and now I'll write it from A to B, kind of like this, is going to be lambda divided by 2 pi epsilon naught, and now it's going to be the natural log of r evaluated at A and B. Now we can also look at a large conducting rod right here, or a conducting cylinder is a better word for it, and make the same argument that we had for the sphere, and that in which case the electric field inside of it is going to be equal to 0. The voltage inside must be equal to then a constant, and that's going to be the voltage at this radius r. We can apply this concept of potential to things that we're already familiar with, rings of charges. I'll leave this one up to you to take a look at for the sake of brevity, example 23.11. As well as a line of charge, which we're already familiar with the electric field from the previous chapters. So take a look at example 23.12. I'll skip it here just for the sake of brevity again. The next concept that I'll talk about briefly is going to be equipotential surfaces and electric field lines. Essentially, an equipotential surface is a surface on which the electric potential is going to be the same. So this is very similar to when you look at, say, a topographical map or a topo map. You see lines of constant elevation where, say, the elevation is always 1,000 feet. Then you see another line when it's 1,200 feet, 1,400 feet, and so on and so forth. The same is going to be true for electric or equipotential surfaces, except we're looking at where there's going to be a constant potential or constant voltage, if you will. So if you look at just a single positive charge, we know that the potential at the charge is going to be positive, and it's going to decrease as we move further and further away from this positive charge. Here we're drawing the electric field lines here in red, I just drew mine in green, and the lines of constant potential are shown in blue here. And essentially this line right here is going to represent where the voltage is always going to be 30 volts. It's always going to be some constant radius away from this guy. This blue line right here might be 50 volts. The next one in would be 70 volts. Again, corresponding more or less to elevation changes on a topographical map. The shapes can look kind of funky if we have a dipole, which is going to be a negative charge here and a positive charge here. But the concept is still the same. All of these blue lines are going to represent a line of constant voltage, say 70 volts. This one over here might represent, say, negative 30 volts, and so on and so forth. Two positive charges is going to look even funkier. We're going to see lines of constant potential, but as we get further and further away from this guy, you can see that these two charges are going to start looking more and more and more like a point charge, and if we move infinitely far away, this oblong ellipse is eventually going to look close enough to a circle that we can treat it as such. Two things to keep in mind, or one important thing to keep in mind, is these electric field lines and these electric equipotential surfaces are always going to be perpendicular where they meet. So that's a fairly important concept. You can kind of see that here. These guys are going to be circles. These guys are roughly circles. If we look at the line of constant voltage where the voltage is 0, as we calculated earlier, this line is going to be, in a perfect world, straight up and down, perpendicular to these electric field lines every place that they meet. So how do equipotentials relate to conductors? If all charges are at rest, the surface of the conductor is going to be an equipotential surface. So it's going to be some line of constant voltage, or constant potential, constant voltage, if you will. We know that now why is this? If you kind of look at this drawing right here where we have our lines of equipotential surfaces, you can see that the electric field is always coming into this conductor right here at a right angle to it. The electric field is always going to be perpendicular to a surface when all charges are at rest. What this also means is the entire solid volume of the conductor is going to be at the same potential, which is what we found earlier. Now, if you think about why we must have an electric field that's going to be perpendicular to the surface, we cannot have an electric field going off in this direction. Why? Because this component of the electric field would have a force. It would move a charge. And up here we're stating all charges are at rest. So the electric field can always only be in the perpendicular direction, and we can have no parallel component of the electric field at the surface of a conductor. The last thing I want to introduce is a potential gradient, very important concept. You'll see this in electrical engineering, you'll see it in fluid mechanics. Potential gradient is a vector operator. It looks like an upside down triangle right here, and you might see it written as del or as grad. What this operator is going to allow us to do is it's going to allow us to write our electric field if we know what the potential is. The potential, or the electric field, is going to be the negative gradient of the potential, where this is a vector, this is a vector operator, it produces a vector, and this is actually a scalar. Now what this operator is going to do is it's going to take partial derivatives of v with respect to x, y, and z, and kind of correspond those to vector directions I hat, j hat, and k hat, x, y, and z, if you will. So really we're saying that the electric field is going to be equal to the negative. It's going to be partial derivative with respect of potential with respect to x. That's going to be in the I hat direction, plus the partial derivative of potential with respect to y in the j hat direction, plus the partial derivative of potential with respect to z, and this is going to be in the k hat direction. These partial derivatives are essentially we're taking a derivative with respect to x and we're holding all other variables constant. So if there is a y in our expression for voltage, we treat that as a constant and we only take derivatives with respect to x. Because these partial derivatives are related to the slope, what this is also kind of implicitly saying is that the electric field is going to be perpendicular to the lines of equipotential surface.